So let's talk about this hydrogen emission spectrum. When you look at a rainbow, that's what we call a continuous spectrum. It's when white light is passed through a prism, it contains all of the wavelengths of visible light. If you take hydrogen gas and you excite it, or if you take like a neon tube, right? That's the same process. You're going to electrically excite this gas. It doesn't have to be excitement from an electrical process. It could be thermal, like in a firework. But you're going to see, instead of a continuum, you're going to see what's called a line spectrum. Only a couple of lines are visible, and each line corresponds to discrete wavelengths of light, and those discrete wavelengths of light are going to correspond to these transitions from one racetrack to another, from one orbit to another orbit, because only certain ones are allowed. Right, so that's why we're only going to get particular wavelengths of light out. This indicates that the energy of the electron on the hydrogen atom is quantized. Right, so that's where our quantumizing is coming when we're talking about emission spectrum. It's how each of those steps is going to be discrete, and it's always going to be the same. The change in energy from a high to lower level of given wavelength can be calculated by E is equal to h nu, or h times c over lambda. What does this look like? Well, if I take like an arc source or the sun and I pass that through a prism, I'm going to get all the wavelengths of light out. If I take my high voltage source and I got a hydrogen discharge tube, I send that guy through a prism, and it's going to kind of look pinkish if you look at it, but if we pass it through the prism, we do some wavelength analysis, we're going to just see 1, 2, 3, 4 visible lines. So 410, 434, 486, and 656. Right? And those are corresponding to those energy level transitions. Each element is going to have its own unique emission spectrum. There is a technique called atomic absorption and atomic emission spectroscopy. And if you take analytical chemistry lab with me, we will do that experiment where you are going to identify a different material based on what its emission spectrum is. Right? And you can kind of do this with the old Mark I eyeball when you talk about something like the alkali metals. So lithium is going to give you a nice red flame. Sodium is going to give you a bright yellow flame. Potassium will be bluish, purplish. Copper, if you take some copper sulfate and burn it, it'll be green. That's how fireworks work. Right? So this color here in sodium, and if we look up here in sodium spectrum, right, we've got some other lines that are really faint, but we've got these two really bright yellow ones here, and that's very distinct and unique for sodium. If you look at lithium, right, so lithium was kind of that reddish color, right, we see kind of an orange and kind of a red line here. And potassium has some red guys and some blue guys. Right? So why is it significant that the color emitted from a hydrogen emission spectrum is not white? That's because it is showing us that the emission of those photons is coming in discrete energy levels, because we only have 4 visible transitions, meaning there's only 4 visible levels, and that they're always going from one level to another, and that energy difference is always the same because the color is always the same. And how does the emission spectrum support the idea of quantized energy levels? If it didn't, and those energy levels were variable or continuous, we would see a full spectrum, we would see a continuum spectrum. So the electron in a hydrogen atom moves around the nucleus only in certain allowable circular orbits. This is Bohr's model. Bohr's model gave the hydrogen atom energy levels consistent with the hydrogen emission spectrum. The expression for energy levels available to the electron in the hydrogen atom can be expressed as E, or energy, is equal to minus 2.178 times 10 to the minus 18 joules times Z squared over N squared, where N is an integer and Z is the nuclear charge. Right? There is another equation called the Rydberg equation, which will be just for the hydrogen atom, and it will describe those energy transitions. Right? As the electron gets closer to the nucleus, E sub n becomes larger in absolute value, but also more negative. The ground state is the lowest energy state of the atom, and an excited state is an energy state in which n is greater greater than 1. Right? So you're taking an electron that's going from a low energy state up into a higher energy state. Right? Starting off low and lazy, you give it some more energy, maybe it absorbs a photon, maybe you thermally excite it, maybe you apply a voltage, it gets more energy and it can move up into a higher racetrack. So if you think about like if you have ever run track and you want to pass somebody on the outside of a curve, you got to run a little bit faster on that outer track, right? So it takes more energy. Right? Each spectral line corresponds to a specific transition. Electrons moving from ground states to higher states require energy, and an electron falling from a higher to a lower state releases energy. And so it's like falling down the stairs, right? It's going to take some energy to go up the stairs, but if you fall down the stairs, you're releasing energy, and you're probably screaming a little bit as you're doing it. Bohr's equation can be used to calculate the energy of these transitions within a hydrogen atom. It gets a lot more complex really fast as soon as you get away from the hydrogen atom. So as long as if you're talking about even something like helium, where you've got a 2-electron system, it becomes way more complicated. We're not going to get into that math at all. All right, so let's look at some of these transitions. So here's an energy level diagram for the first 3 electronic transitions. These are the ones we can see. So when we're talking about these energy levels, we've got energy level number 1. That's our ground state. Right? It's low energy. And then there's a big gap between energy levels number 2, and then these gaps kind of get smaller and smaller and smaller as they go to 3 and 4 and 5. Right? So the difference between 4 and 5 is less than the difference between 4 and 3. Right? The ones we can see, right, the transitions that we are able to see are the ones that go from n equals 3 to 2, 4 to 2, 5 to 2, and 6 to 2. Those are the 4 transitions that we can see as visible photons. Is there a transition between 2 and 1? Sure, there can be. But this big gap here means that there's a lot of energy. If it's a lot of energy, it's a short wavelength. That's actually going to be in the ultraviolet. So people will use hydrogen lamps as an ultraviolet light source sometimes. If you look at the transition between 4 to 3, that's a lot smaller, or 5 to 3. These something where they end up at 3 transitions are going to usually be in the infrared. They're a lot less energy. They're below the wavelengths that we can see. So let's look at some of these and we'll map them out. So if you look at here our orbit transition diagram, right? And you look, here's our orbit. It's going from 5 to 2 or 5 to 1, right? You get a transition here, and you get a little bit shorter transition going from 3 to 2, and then a little bit less energy going from from 3 to 2, and then this one's 4 to 2, that one's 5 to 2. Right? So you get different amounts of energy, and that's giving us our different line spectra. Right? And so this is showing the orbital diagram here and the corresponding emission spectrum over here, which you would see on a photographic plate. When the hydrogen atom returns to its lowest possible energy state, that's called the ground state. That's when n equals 1. When the electron falls from n equals 6 to n equals 1, delta E can be computed by the energy of the final state minus the energy of the initial state. Anytime you see this delta, right, it's almost always going to be final minus initial. We're going to see lots of delta E things going in here, delta E, delta H, delta G, right? These all mean final minus initial. So if we're looking at the energy from the initial state to the final state to the initial state, we're going to look at our energy from our initial state minus the energy of our final state, and we end up with negative 2.117 times 10 to the minus 18 joules, with a negative sign indicating that the atom has lost energy and is in a more stable state. The minus sign is also going to tell us about the direction of energy flow a lot of the time. So this minus sign means that energy has left the atom. It's going to leave that atom as a photon. If you went from 1 to 6, that number would be positive, indicating that the atom has absorbed or taken in that much more energy. The energy lost is taken away from the atom by the emission of the photon, whose wavelength can be calculated using our E is equal to H times nu, or E is equal to H times C over lambda. And we can rearrange that to solve for lambda. So our lambda is going to be H times C over our change in energy. Delta E, the change in energy of the atom, is equal to the energy of the emitted photon. So our lambda, our wavelength of energy of the photon emitted, is going to be h times c over delta E. So 6.6 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8th meters per second divided by 2.117 times 10 to the minus 18 joules gives us 9.383 times 10 to the 8th meters. Calculate the energy required to excite the hydrogen electron from n equals 1 to n equals 2. Also calculate the wavelength of light that must be absorbed by a hydrogen atom in its ground state to reach its excited state. So we're going to use the equation. E is equal to minus 2.718 times 10 to the minus 18 joules times z squared over n squared, where z is going to be equal to 1. We're going to have for energy level 1, minus 2.178 times 10 to the minus 18 times 1 squared over 1 squared, which is minus 2.178 times 10 to the minus 18. For energy level 2, it'll be minus 2.178 times 10 to the minus 18 joules times 1 squared divided by 2 squared, or negative 5.445 times 10 to the minus 18 joules. We're then going to look at the difference, final minus initial. In this case, final is going to be 2, and initial is going to be 1, so negative 5.44 times 10 to the minus 19 minus 2.178 times 10 to the minus 18 is going to give us positive 1.633 times 10 to the minus 18 joules. The positive value for delta E indicates that the system has gained energy. The wavelength of light that must be absorbed is going to be proportional to that energy. So our wavelength is going to be h times c over delta E. So we're going to do 6.6 times 10 to the minus 34 joules times seconds times 3 times 10 to the 8th meters per second divided by 1.63 times 10 to the 8th joules, or 1.216 times 10 to the minus 7 meters. The importance of the Bohr model is that it correctly fits the quantized energy levels of the hydrogen atom, and it postulates that only certain allowed circular orbits for the electron. As the electron becomes more tightly bound, its energy becomes more negative relative to the free electron. The free electron is at an infinite distance, at the infinite distance from the nucleus, and it's going to have no nuclear attraction. As the electron is brought closer to the nucleus, the energy is released from the system. The general equation for the electron moving from an initial to a final energy state can be derived from the following equation, where we've got that E is equal to 2 minus 2.178 times 10 to the minus 18 z squared over n squared, right? And so we can generalize this for a final minus initial. We're just going to follow through some of that math, and we end up with minus 2.178 times 10 to the minus 18 joules, 1 over n squared, so final minus 1 over n initial squared. So this is what we're going to use to calculate that difference in energy. Note that this model works only for hydrogen, and electrons do not move around the nucleus in circular orbits. If you think about a charge rotating in space, you're going to be ending up radiating energy out doing that. And so, that model only works so far. The physics kind of fall apart when you start to examine some of it. It makes for a really great logo, right? So if you're living in like the atomic age, 1960s, and you got all those nice little atom pictures on there, it is awesome, but it's not necessarily a very accurate representation of what electrons really look like. And so what we learned from this is that energy levels are discrete or quantized, right? So I've got a ground state, and as I go from a ground state up to a more excited state, that is going to take energy. The amount of energy it takes to keep going up subsequent levels is going to decrease. The emission is going to follow the opposite process. As I go from an excited state to a less excited state, I'm going to have to give up energy to get down to a more relaxed state. Just like human beings, man, like let it go. Like you got to give off all that negative energy to reach that ground state, man. So you got to be able to like give off some energy. That energy is going to come out in the form of photons, if you're talking about an electron, and like bad vibes, man, if you're a human being. For our hydrogen atom, we said that our transitions between n equals 3, 4, 5, and 6, those are our visible ones. And then we've got some that are in the ultraviolet and some that are in the infrared. So here we've got some that are in the visible, they're ending at n equals 2. Our infrared guys are going to be ending at n equals 3, and our ultraviolets are going to be ones that are ending at n equals 1. They've got different names. I do not expect you to know them. The visible ones are called the Balmer series. Then there's the Passion for the IR, the Lyman series for the ultraviolet, and then the far infrared is going to be the Brackett series, but you don't need to worry about that. Just that it's there. All right, so let's take a look at what we've got. So summary of the major observations and theories that have led from classical theory to quantum theory. So classical theory says that matter is particulate and massive, and that energy is continuous and wavelength. And since matter is discontinuous and particulate, perhaps energy can be discontinuous and particulate as well. And so that's our transition from our classic to our theory. Is that maybe energy is going to act like a little bit like matter. So we've got a couple of things backing that up. So we've got the black body radiation experiments, and that was Planck showing that energy is quantized and that only certain values are allowed. So you could also throw in, you could do Planck, you could do Bohr in there as well if you wanted to. You got the photoelectric effect from Einstein, which shows that light has particulate behavior. It can act like a ballistic photon or a ballistic particle. And then you got the atomic line spectra from Bohr showing that the atom's energy is quantized and that a photon is emitted when an electron changes orbits. You got 3 lines of evidence that are now showing us that this energy, right, these things that we think of as energy and traditionally wavy things, are actually going to act a little bit more like matter. They're going to act particulate and massive. And so this is our transition from classical to quantum theory. Then you got to ask, well, if energy is wave-like, right? So instead of thinking of energy as continuous and maybe it's going to act particle-like, what if I think about that from the flip side and say, well, if we think about matter, maybe it's going to act like a wave instead. So we've got a couple of different observations. So Davison-Germer had an electron diffraction by a metal crystal. So they were able to send a beam of electrons into this crystal, and if the electrons acted like particles, they would just bounce off. But what they were seeing was a diffraction pattern like you would see if the electrons were acting like a wave. And so Bruy said, well, maybe since all matter travels in waves, the energy of an atom is quantized due to the wave motion of the electrons. And since matter has mass, perhaps energy can be massive. Right? So Compton did experiments with the photon. So as the wavelength increases, the momentum decreases after colliding with an electron. And Einstein, de Bruy said that the mass and energy are going to be equivalent, that particles are going to have wavelength, and photons are going to have momentum. And so this brings those 2 lines of thinking together in something that we call quantum theory that says energy is the same as matter. They're both going to be particulate. They're both going to be massive, and they're both going to be wave-like. Right? So Bohr could not explain why electrons were restricted to these fixed distances around the nucleus. Like, why wouldn't that electron be at some arbitrary distance? Right? And de Bruy reasoned that if energy, and this was in 1924, right? So this is after the First World War, a little bit before the Second. If energy can behave as a particle, then perhaps particles like electrons can exhibit wave-like characteristics. And so he was around until 1987. And so de Bruy proposed that electrons in atoms are going to behave like standing waves, like the wave created when a guitar string is plucked. And that there are going to be some points, which we call nodes, where wave exhibits no motion at all. If you think about a guitar string, right, so you've got a certain wavelength, and you can have a full wavelength. It's going to occupy the full thing. And you can have 2 half wavelengths. Right? There's a node in the middle. This spot in the middle is a node. You can have 3 half wavelengths that fit. But if you try to do 3 1/3 or 2 1/2 or some arbitrary number where they're not going to be able to double back on each other like this, you're not going to be able to support that. So if if you think about that guitar, you've got your primary note, you've got your first harmonic and your second harmonic, right? You've got your overtones. And if you, instead of putting this on a string on a guitar in a linear way, you put this on a circle instead. You basically take this end and you wrap it around to this end, right? You can see that you can support an n equals 3, right? 3 half wavelengths. Or you could do 5 full half wavelengths. But if you try to do 3 1/3, the ends aren't going to match up. So only certain multiples or discrete intervals are going to actually work to maintain that standing wave. So de Broy's idea of a particle and wave properties are going to be related by the following equation, which says that lambda, our wavelength, is going to be equal to h divided by m times u. Right? So notice that this is going to be what we call a de Broy wavelength. This is not the wavelength for a photon. Right? It's going to be related to m, the mass, and then u, the velocity. And this is another one where people commonly get tripped up, is that they will try to use that E equals h nu, and they'll mistake this u for velocity or a v for velocity for a nu. Right? And they'll pick the wrong equation. So if you're talking about mass, this is the one you want. Right? You want the de Broy equation. So for example, here's the de Broy wavelength of several objects. The de Broy wavelength is going to, if you look at it, this equation is saying that the bigger you are, the smaller your wavelength. The faster you are moving, the smaller your wavelength. So if I take a slow electron and a fast electron, they've got the same mass, but one's moving at 1 meter per second and one's moving at 6 times 10 to the 6 meters per second. That slow one is going to have a wavelength of 7 times 10 to the minus 4 meters, and this fast electron is going to have a much smaller wavelength of 1 times 10 to the minus 10. If I look at a 1 gram mass moving at by 0.01 meters per second, that's going to have a very small de Broy wavelength, 7 times 10 to the minus 29. If I take a baseball, right, and I move it at 25 meters per second, its de Broy wavelength is going to be 2 times 10 to the minus 34 meters. So that's why we do not see things on the macro scale as being wavelengths. Right? We don't see things like baseballs or 1 gram masses as acting in that kind of weird quantum wave-like way, because that wavelength is so small. It's smaller than what we call the Planck length, but it's there, and it's just, you can't perceive it, that it is so small. And if you take the Earth, which is moving at 3 times 10 to the 4th meters per second, and it weighs a lot of grams, 6 times 10 to the 27, you're going to end up with 4 times 10 to the minus 64 meters as its wavelength. So it is a very, 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 very small wavelength. So let's look at an example. Calculate the de Broy wavelength of the particle in the following two cases. You got a 25 gram bullet traveling at 612 meters per second, or an electron moving at 63 meters per second, where 1 joule is equal to 1 kilogram times meter squared per second squared. So for a bullet traveling at 25 gram bullet traveling at 612 meters per second, we've got our h, our Planck's constant, right? And then we're going to divide it by the mass. And we're going to convert our 25 grams into kilograms, 0.025 kilograms. And we've got our velocity, 612 meters per second. And that's going to give us 4.3 times 10 to the minus 35 meters. So a very, very small wavelength. If we take an electron, whose mass is 9 times 10 to the minus 34 kilograms, and so very, very light, and it's moving at 63 meters per second, quite a bit slower, its wavelength is going to be 1.16 times 10 to the minus 5 meters. The wavelengths for our macroscopic particles are imperceptibly small and have no real physical significance. Now, why is this important? Right? As a consequence of de Broy's work, we now have techniques such as X-ray diffraction and electron microscopy to study very, very small objects. So electron diffraction, right, that gives us the structure of DNA. It can tell us about molecular structures. Electron microscopy lets us look at very, very small things. There is something called the Abbe diffraction limit, which for an optical microscope means that you cannot get a resolution smaller than half the wavelength. So, if you're looking at something with a blue light, you could only resolve features that are 200 nanometers big. Well, lots of things are smaller than 200 nanometers. And so if you want resolution smaller than that, you can use an electron microscope to beat that diffraction limit. You want to increase the magnification, you want to get higher resolution, you just accelerate that electron a little bit faster in your electron microscope. That's going to shorten the wavelength, it's going to increase your resolution, which has the effect of increasing your magnification. Okay. So scientists want us to know exactly where the electrons are in an atom. The problem with that is we run into something called the Heisenberg uncertainty principle, which mathematically describes the position and velocity of an electron. The more you know about one, the less you know about the other. So if you know where the electron is, you don't know how fast it's going. If you know how fast it's going, you don't